Yeah. So let us begin the session. So as you know, we have been discussing advancement in topological K theory, and the speaker is Professor Somnath Basu from IISc Calcutta. He is going to continue his discussion on Bott periodicity.
Okay, thank you, Dipankar. So yeah, so I'm going to recall a few things from last time just to set up the context, and then we'll try to follow a proof of Bott periodicity as outlined in this article by Aguilar and Brito. So I'll give you the basic steps. Some of the details you have to check, but hopefully that should give you a proof of Bott periodicity. Okay, so a bit of recap, let's say. So we had defined, remember, our K groups was defined to be, well, at least this was one definition. Right, the homotopy class of maps from X to Z cross BU, and K tilde could be defined as the co-kernel, or you could define it for a base space by essentially looking at K of X0, which is a copy of Z and modding out. But nonetheless, here's a succinct description of K tilde X. It's the homotopy class of maps from X to BU, where, as we have argued last time, for every group there is a space called BG, the classifying space, and it's universal in the sense that it classifies principal G bundles over reasonable spaces like paracompact spaces. So this is what BU is. U itself is the co-limit of the unitary groups UN, where UN sits inside UN plus 1 by adding a 1 in the block diagonal form, adding a 1 in the n plus 1 cross n plus 1 entry. Okay, so let's see what we are interested in. So the point is that you are interested in this object. And what is Sx? Remember, Sx is, let's say if you're in the base setting, Sx is the reduced suspension. So this by definition is going to be mapped from here to here, but there is an adjunction, and the adjunction sort of tells me that this is the same thing as x comma omega bu. So let me so this is coming from an adjunction, right? What is this adjunction? Well, this adjunction, let me use a different color. So this is essentially this fact that if you have a map from suspension to y, what is the suspension? This is exactly the same thing, and we talked about this last time. You can obtain this suspension by smashing x with S1. So look at S1 cross x, and then you collapse the two ends, the two end copies of x, and then if there's a base point, you collapse the line corresponding to that base point as well. Okay, so yeah, if there are any questions in the chat, in case I miss it, please let me know. So that's what this is. So it's the same map, but now you see that this will actually sort of imply either way a map f tilde from x. So for every point in x, you have a copy of S1, and f, when you freeze the second variable little x, you get a map from S1 to x, and these are base maps. So it lands inside omega y. Okay? And then if you have homotopies of f, then you get homotopies of f tilde. So this correspondence f to f tilde is what we call the adjunction, and that's what gives you this this thing over here, right? So that's what gives you this particular equality that I mentioned as adjunction. Okay. Okay. So if we apply this further to k double tilde of S2 of x, what do we get? Well, we get we apply this further. apply this to S of x. So this is Sx comma omega bu. But applying that junction once more, this is x comma omega square bu, right? Okay. And what are we interested in? So if we can if we can somehow show that omega square bu, the double loop space of bu, is homotopy equivalent to bu itself, then we are done. Because then this is, if this is equal to x bu, then this is nothing but k tilde of x. We wrote this thing slightly differently last time. We said k tilde of the suspension is nothing but k tilde of s, the reduced k tilde of s2 tensor the reduced k tilde of x, but the reduced k tilde of s2 is just copy of z tensor z. So that was the isomorphism. This is in a different way the same isomorphism. So this is what we're after. We are asking whether omega squared bu is homotopy equivalent to bu. What we'll show, in fact, is there's another homotopy equivalence which Bott originally proved, which implies this statement as well as the periodicity statements of homotopy groups that you might be more familiar with. Okay, so here there are two facts. So let me outline them. Which ones are? Okay, so two facts. Say fact one, and this is easy. This says, and we'll actually give a proof of this fact. This is true in general, that there's a homotopy equivalence between omega bu and u. Okay? And you should note that this homotopy equivalence is not just any homotopy equivalence. It's going to be a homotopy equivalence. I mean, this is induced by a map, which is a map of H spaces, let's say, or map of groups. Okay? Although omega bu is not quite a group, but it's a group-like map. So that's going to be useful. And then there's this other fact, fact two, and this is sort of the non-trivial. Okay. And this basically says that Z cross Bu is homotopy equivalent to omega U, right? Okay. So this is essentially what Bott proved. Okay. Okay. Excuse me. Sorry. So let me state a couple of consequences before we actually sort of state the version that Aguilar and Preto proves, and what are the topological preliminaries that go into setting up that statement. Okay. So here's a couple of consequences. Consequence one, of course, is you have that U is homotopy equivalent to omega Bu, right? But you see, this is the same thing. See, Bu is connected, right? So if I have a space which is not connected, when I take its base loop space, I'm effectively only looking at the base loop space of a component of that space. The entire space doesn't matter because base loops are loops based at a particular point. So in this case, this is the same thing as omega of Z cross Bu, because I could simply think of Bu as sitting inside Z cross Bu as the zeroth component of Bu. So 0 cross Bu is a copy of Bu sitting inside Z cross Bu. And as far as base loop spaces are concerned, they're fine. But this now I can use Bott's result. So this is saying that this is going to be, let me put it this way. This is, well, I could, fine. So this is homotopy equivalent to omega square of U, right? Okay. So this in particular tells me that if I'm calculating the homotopy groups of U, the infinite unitary group. This, because taking omega shifts everything by 2, this tells me that this is J minus 2 of U, right? So interested in the homotopy groups of U, I am effectively asking whether I know pi 0 and pi 1. Okay, and pi 0 is trivial because U is connected, and pi 1 is the only other odd homotopy group of U because of this twofold periodicity, and pi 1 of U is Z because pi 1 of UN is Z, and that stabilizes. Okay, so this effectively tells me that the only thing which are of interest to me would be, let's say, pi 0, which is 0, and pi 1, which is Z. So these are the, and every other group, just it's a parity thing. So pi 2 is 0, pi 3 is Z, and so on and so on. So that's one immediate consequence. There are similar periodicity for BU as well, because BU is connected to omega BU is connected to U, and U is connected to omega BU. Okay, all right. Okay, are there any questions? All right, so now let me consequence 2. So consequence 2, which sort of would be the Bott periodicity statement. It's the fact that let me put it differently. Let me start here. So we have BU, and this is B omega BU. Okay, and this we'll see is basically, so this is usually not true, but this will be true because the map from U to omega BU is a group-like map. So it induces a map from the classifying spaces. So this is a homotopy equivalence. Okay, and then this, as you know, is B. Sorry. Up. So this is omega of Z cross BU. Again, this is something we already used, right? So at the level of spaces, omega BU and omega of Z cross BU are the same. So you can apply B, and you get this because, and then this is nothing but, I guess, B of omega square of U. Okay, and this will turn out to be the same as omega square of BU. Okay, so in other words, you can show that k tilde of x, if you go up, k tilde of x and k tilde of S2x are same. Okay, all right, sorry, it went up. Okay, so that's the my starting point about just a second. Yeah, so now let me state the theorem of Aguilar and Preto, which proves this particular thing, this one, the one that we want to highlight, which is, let's see, this one. Okay, all right. Okay, so let me state the theorem straight away. So this is the theorem. Okay, and what they say, the following. So let me use a color. So they say that, and I'll explain at least one of the terms which many of you may not have seen. They say that there is a quasi vibration or quasi vibration. So yeah, so my writing might be a little slower than usual because it's somebody else's tab that I'm using. So sometimes the pen is switching between the eraser and the writing, so I apologize for that. Just bear with me, okay? So there is a quasi vibration P from E to U. U is again always going to be the unitary group in this talk, no matter how it's defined, such that two things happen. Okay, such that E is contractible and P inverse of U. So U is anything here is Z cross. So let me write it this way. I think this is better. The fibers. Okay, so this is the theorem that we're going to sketch. And we're also going to first start off by recalling some basic topological constructions involving fibrations, quasi-fibrations, and bundles, and then indicate why this proves Bott periodicity. Okay, so why this implies that Z cross BU is homotopy equivalent to omega U. Okay, and then we're going to outline the relevant steps in the proof. Okay, all right. Okay, so now we're going to go back, and so this is going to be basic constructions. Okay, I mean, some of you may know these, some of you may not, because your background may not necessarily be from topology. So if you have seen these, just bear with me. We'll get into interesting things hopefully soon. Okay, so the first one that I want to talk about is called the path space construction. It's kind of a very simple looking construction, but in terms of its impact, it's one of the most important constructions in topology and geometry. Okay, so what this is you look at, so for any base space, so you start off with base space, and assigned to this you construct px. So this is called the based path space. So this is by definition all maps from I to x. Okay, so these are all paths starting at x0. So if you want a picture, the picture would be something like, here's your x, and let's say here's your, this is one path, this might be another, this might be another, and so on and so forth. This might be another, and then this is sort of your x0, right? So look at all these paths, and that's what this path space is, right? And it has the compact open topology because it's a subspace of maps from I to x. And there is a natural map called the evaluation map. And what it does is, if you give me a path, I send it to its endpoint, gamma of 1. It's clearly, and assume x is path connected. So it's a surjective map. And it turns out that this is actually a fibration, a Hurewicz fibration. So this is, which, if you don't know what fibrations are, this simply means that it admits homotopy lifting with respect to all spaces. Okay, so we'll mention homotopy lifting once more when we actually get to it. But think of these as slight generalizations of fiber bundles. Yeah, okay, fiber bundles are locally trivial, and fiber bundles are fibrations, but fibrations need not be fiber bundles. Fiber bundles are more aligned to geometry. Fibrations are more aligned to topological and homotopical constructions. Okay, it's a fibration with, with fiber. And what's the fiber? Fiber is the homotopy type of the fiber is the same. So you just take evaluation inverse of, let's say, the point x0 itself. Then what do you get? You get all paths starting and ending at x0, because gamma of 1 has to be x0, which is nothing but our base loop space. Recall that this is the space we had constructed, omega x0, and this is that, it's the based loop space. Right? So this is one important point. The other important point is this px is actually contractible. That's important. So you're constructing a large space which is actually contractible, and a physical contraction is obtained by simultaneously shrinking all the paths down to x0. Okay, and so you can write that thing down. It's going to be a map from px cross I to px. And what is it going to do? If you give me gamma and you give me a time s, I'm simply going to send it to a new path, and the path is gamma of 1 minus S T. Okay, so this is going to be my assignment. So gamma comma S goes to the path T goes to gamma. So at S equal to 0, this is sending gamma to gamma. At S equal to 1, this is sending gamma to the constant path at x0. So this is indeed a contraction of px to the constant path at x0, and hence px deformation retracts to the constant path at x0. Okay. Okay, great. So this is one sort of. Oh, by the way, I should probably mention a reference for this thing. So okay, I'll just remind me at the end. I'll mention this and some other references. I mean, it's only one paper by them. Okay, so this is the first construction. Okay, path space construction. So now we're going to do another one, which is very similar, and many of you may have seen this, but you may not have. So let me just set the stage for that. So classifying space. Okay, so this construction in modern terms works for pretty much a large plethora of things, including groups, including group-like spaces, including categories, including monoids, including algebras. But we are going to stick to the standard classifying space of a nice topological group, let's say. Okay. So what is this saying? So this is saying, let me use the same color. So this is saying that we can construct a universal principal. And you'll see in what sense this is universal. G bundle of the form EG, who maps to BG. This is G. Okay. So this thing over here, this universal, sort of could be equivalently thought of as saying that your, let's say this is the same thing as saying that your EG is contractible and G acts freely on it. And then the quotient is what you define to be BG. Okay, so effectively you are looking for a space which is contractible and on which the group G acts freely. And it is going to turn out to be universal in the sense that any principal G bundle over reasonable spaces are classified by maps to it. Okay, so I mean, it turns out that, sorry, so it turns out that any G bundle, let's say P over X, can be obtained as P is going to be obtained as F star, the pullback of this bundle via sum F from X to BG. So if you have a map from X to BG, since there's a G bundle over BG, this one, you pull that back, that's also going to be a principal G bundle. So this F is called the classifying map, or rather the homotopy class of F is called the classifying map, and hence the name universal principal G bundle. So such things exist, and if you, for those of you who haven't seen how this is constructed, well, the idea sort of goes back to Sugawara, maybe even others before him, but Milner was the one who sort of, you know, clarified the proofs for, let's say, good groups and so on. And the proof sort of goes in the following direction. You sort of look at G, and then you look at G star G. So this is the join construction. So you take two spaces, and the join of two spaces is literally the space of all line segments joining a point in X to a point in Y. And you can give it the appropriate topology if you can embed everything in Euclidean spaces. You can take joins, and it turns out there are inclusions, natural inclusions. And so you take this co-limit and you define that to be EG. This is the co-limit of G star. Okay. So again, you have to check certain things that this is indeed contractible. That is probably not hard to imagine in an example that I've outlined just now. But more so, you have to show that G acts freely on this, which is also rather easy. But you just don't want G to act freely. You want it to act freely so that the quotient is nice. So that is usually not for free if your G is not a discrete group. And so that requires a little bit of work and changing the topology, which Milner clarifies in his paper. If your group, because you cannot just take the topology of the join, you have to modify it a little bit, okay? But you could take an example and see what happens. So, I mean, just to give you an example. So if G is S1, what is S1 join S1? We know that S1 join S1 is nothing but S3. And then S1 join S1 join S1 is nothing but S5. So this thing here is S3. This will turn out to be S5 and so on. So these inclusions are the odd spheres included into the next higher spheres, okay? And what is the group action? Well, the group action is acting simultaneously on both the factors. So you know that when you pass to, no, so when you pass to quotients, mod S1, mod S1, and so on. Again, this is an example. If you have seen it, fine. If you haven't, you can ignore it safely. So if I mod S1 by S1, this is just a point. If I mod S3 by S1, what I get is S2. This is just a half vibration. If I mod out S5 by S1, this is a half vibration, but now to give me CP2. This is secretly CP1, and it keeps going, okay? So my BG for this case is going to be the limit of these, and you can imagine what the limit of these are. The limit of this is the infinite CP thing, right? So this in the limit is S infinity, and this in the limit is, and this is my BS1, right? So this particular thing is B. This is the universal space classifying principal S1 bundles, okay? Okay, fine. So this is the second. Out is in both cases you're constructing bundles, either a fibration or a principal bundle, where the total space is contractible, either the path space or EG, and the fibers are whatever they are in the cases. Okay. Okay. So now I want to state a result, which is a way to compare comparison of, let's put it this way, fibrations. Yeah. Okay. Okay. So we're going to start. So I'm going to skip the definition of quasi-fibrations for now. It's not too important what it is. It's a slightly more flexible version of fibrations in the sense that you do not ask for homotopy lifting, but you still require long exact sequences and the usual stuff to go with. Pretend for the moment that quasi-fibrations are fibrations. I'll give you a specific definition in a moment. Okay. So the setting is as following. You have a quasi-fibration which is of the form F to E B, this is P, and you have a genuine Hurewicz fibration. So there are usually two types of fibrations in topology. Hurewicz fibration means the homotopy lifting is true for all spaces. Serre fibration means the homotopy lifting is true for CW complexes. We are going to assume that the lifting is true, holds for all spaces. So you have this on the one hand, and then you have a fibration which is of the form F prime to E prime to B. So note that the base spaces are the same. I am requiring both these to be fibrations over the same base space B. And I'm going to assume that this is the total space of the quasi-fibration is contractible. I'm assuming that, okay? So now now because it's contractible, what is the first thing you can do? So the first thing you can do is you can define a map from, you can define a contraction, right? So H at time 0 maps all of E to, let's say, E0 prime. Do I want that? Well, okay, not E0 prime, rather I would be happy calling it E0 because the primes are taking values elsewhere. Okay, and H at 1 is the identity of E. That's what a deformation retract means, right? That space deformation retracts to a point. So there is such an H because E is contract. So now that there is such an H, what is the thing that you can do? The thing that you can do is obviously what you must do, which is look at E cross I, and there's a map from here to B. What is this map? I'm saying look at this map H and you compose it with P. So H is a map from E cross I to E, and then you compose with P, that's a map from E cross I to B. On the other hand, you do have a map P prime to from E prime, right? This is just part of the data. And on the other hand, I do have a map from E cross 0. This is the inclusion, right? This is I. So if I can define a map here, right? If I can define a map here, then I'm done. Then I can use lifting. So what can I define? Well, think of what happens, right? If you start with any particular E comma 0 here, this goes to E comma 0 here. This under H goes to E0, and then you simply go to P of E0, right? Which is, let's say, our base point B0. So to define a map here, all I have to do is find some E0 prime, which lives over B0, and simply send everything here to that, right? That would do the job. So of course, there is a map from E cross 0 to E prime. Just send everything to E0 prime, some preimage of B0. Once that is done, homotopy lifting tells me that there is a lift, right? Let me call that H tilde, or let's say just H. Okay, so there is a lift. What does that lift give us? This is just homotopy lifting applied to any space. So we're doing it for E because we don't know whether E is, let's say, a CW complex, but it's a contractible space. So homotopy lifting gives us an H, and I'm claiming that you can restrict H to H at 1. So you look at time 1, it still gives you a map from capital E to capital E prime. And I'm claiming that this will give us a diagram like this, which is you have a map from E. This is H restricted to time 1. This is E prime. This is P. This is B. This is identity. This is P prime. This is B. This is F. This is F prime. And I'm claiming that this square commutes. Why? Because you see, little h at 0 was constant, little h at 1 is identity. So this triangle over here, you see, look at this triangle over here, this triangle, right? This triangle commutes. What does that mean? So that basically means that P prime composed H equals P composed H. So at time 1, what I get is P prime composed H1 equals P composed H1, which is P, because H1 is identity. So this is literally what the square is. And in particular, this also tells me that there's a map, induced map between the fibers, correct? Now we are going to assume that E prime itself is contractible. So far, we do not use that. We only use the fact that E is contractible. So now if you assume if I assume that, what does it buy us? Well, it tells me that this is a quasi-isomorphism because, I mean, it's a homotopy equivalence. This is a homotopy equivalence. So this map has to be a weak homotopy equivalence because I don't know whether, I mean, I can say that there are homotopy groups. This is, so F to F prime is a weak homotopy equivalence. If things are CW complexes, this is a genuine homotopy equivalence. So what we are proving so far, let me recap in short. If I have a quasi-fibration or a fibration and a genuine Hurewicz fibration, where the total spaces are both contractible over the same base, then the two fibers are weakly homotopy equivalent to each other. Okay, so that's what. So let me mention Hurewicz. This is the Hurewicz vibration. Okay, great. So the upshot is this, that there's a, so let's say F okay, good. So we are going to use this in two particular contexts. So we're going to deduce two corollaries of this thing itself. So let me see what color we used. Consequences. Okay, I'll just go ahead with colors. Okay. So corollary A is we can apply this path space vibrations to the space BU itself, right? Think of X as BU, apply the path space vibration. What do you get? You get this, right? But we know that this is contractible, and in fact, the path space vibration is a Hurewicz vibration. Great. We also have another vibration with the base BU. Which one is that? Well, that's the one that we just constructed due to Sugawara, Milner, and others. This is this one, right? So both the vibrations are over BU, the total spaces are contractible. So this tells us that, also it tells us that, sorry, U okay. So this is one of the facts which we claimed was an easy fact. This would be true for any group for that matter by the same reasoning. You just need the existence of the universal bundle, and then you apply the path space vibration to the space BG. So that's all it requires. Okay, corollary B. So this is essentially back to what they actually proved. That. So the point is, what do they construct? They're going to construct a quasi vibration over, I guess this is over U, the unitary group, the infinite. So this is going to be a quasi vibration, and they're going to produce a space E which is contractible. It fibers over U. This is a quasi vibration, and the fibers are Z cross BU, right? But notice that you already have another one. And what is the other one that you have? Well, you have the path space applied to the space U itself. So this is another vibration. This is actually a Hurewicz vibration, and this is contractible, right? So which means, again, by the same observation that we just did, that you're going to get a map from Z cross BU to omega U, and that's going to be a homotopy equivalent. So it maps to the Hurewicz vibration, which this one is, right? So this is, in this case, a Hurewicz. Okay, so this proves the version of Bott periodicity that you started off with. Once you have constructed such a quasi vibration with a total contractible space and fibers being Z cross BU. Okay, so in the rest of the, I guess we started like 5 minutes late. So in the remaining 25, 30 minutes, I'll try to outline the construction of this E and sketch what goes into checking some of the details. Of course, there'll be details that I'll leave off, and you just have to read the paper. It's reasonably readable, given it's not a long paper, but it involves a lot of basic constructions and then checking that things are well defined and they do what they're supposed to do. So that's going to be more or less the plan. Are there any questions so far? Okay, great. So, so we're going to start off. Yeah, so this is called quasi fibrations and sorry. And this was published in topology and its applications, volume 98, I guess, and the year was 19. I believe it's 1999. Anyway, you can search through the title. I might get the dates wrong, but the title and the authors are good enough. Marcelo Aguilar and something Preto. Okay. So I need to define a space first, and then I'll basically outline some maps or spaces which will be relevant, and then along the way highlight some propositions which will be used in conjunction with each other to construct the final space E, the final map P, and then want us to check that E over U is actually a quasi-fibration with the fiber being Z cross BU and the base being U. So one thing that you have to expect immediately, or let's say with a little bit of thought, is that it's not going to produce a space whose fibers are Z cross BU directly. It's going to produce a different version of Z cross BU because the E is constructed out of certain Grassmannians and unitary things. So we're going to use a different model of Z cross BU. Okay? And in fact, there are many different models of Z cross BU. If you look at the proof due to Atiyah and Bott maybe and others, where they use this index of Fredholm operators to connect this with this K theory. One model of Z cross BU is going to be the space of Fredholm operators on an infinite dimensional Hilbert space H. So that's another model for Z cross BU, which is used in another proof of Bott periodicity and also connected to index Sathya-Singer index theorem. So here we're going to use a different model of Z cross BU. Okay? But before that, I need to define, make a definition. So let me so whenever you have this, so you have minus infinity, P, Q, infinity in that order, and P could be minus infinity, Q could be infinity. So you do not want all three to be equal, okay? Not all three equal, okay? And for this, we define the space C, Q, P, which is by definition all okay, such that Zi is equal to 0. Almost all I. So essentially, so the point is, it could be arbitrarily large, but it's essentially going to be 0 for almost all I. And if P or I is bigger than Q. Okay? So this is the definition. So you declare C upper Q lower P to be, so you can think of it as a map from Z to C, but effectively it's just an infinite tuple of complex numbers which are 0 for almost all I, and then whenever either it's that, and whenever I is less than or equal to P or I is bigger than Q. Okay? So just to see what is going on, So if you look at this particular, so you notice that CQ0, this is nothing but CQ, C infinity 0. This is nothing but the usual C infinity. And whenever you have infinitely many of, like if you look at C infinity, what is this? It's the co-limit or the direct limit of C sitting inside C square sitting inside C cube, and the topology is obviously the union of the topology of the union for finite dimensional spaces. So if the space is finite dimensional, C cube P, it has the usual topology. If the space is infinite dimensional, it's the topology is given by the direct limit or the co-limit or the topology of union. So C is infinity 0 is just the usual C infinity. C10 is just the usual C, and C00 is just the zero vector space. Okay, that's what it is. So I'll make a remark, which is probably something you already knew, or you can decipher. So if minus infinity is less than P, is less than or equal to Q, and less than infinity. So if P and Q are not minus infinity or infinity, but actually finite, then it's pretty clear that this thing has dimension, and all of you would know what the dimension is, has complex dimension Q minus P, right? And something more is true. I can look at C cube P, direct sum C R cube, and this direct sum is nothing but CP, because this is essentially the only non-zero entries are from P through Q. This is from Q through R, and exactly like that. So if you sum them, this precisely the space where non-zero entries in the infinite tuple are from P through R. Okay. All right. So that's instruction. Okay, so this is the main vector space that we're going to work with. So all of these vector spaces are contained inside C infinity minus infinity, right? So essentially the full definition when you allow P to be minus infinity and Q to be infinity. Okay, so all right, so now I'm going to outline some maps and constructions. They're all rather basic when you think about it, but because you'll be seeing so many different maps and objects at the same time in a span of 15-20 minutes, this might be a bit overwhelming, but when you go back, look at it, the objects are pretty standard. You just have to check some of the claims that I'll make. Okay. Okay. So let me, how do I want to use a bullet point? Let me use a different color. So, well, okay. So let me put A here. So as far as the classifying space of BUN is concerned, this is rather classical. What is BUN? So it's a space which classifies principal UN bundles. That's the same thing as the infinite complex Grassmannian of n planes inside C infinity, right? So this, you might have seen various models, but this is nothing but the Grassmannian of n planes in C infinity. But as we saw here, C infinity is just C infinity 0, no notation. This is also more commonly thought of as the co-limit of the n Grassmannian of n planes inside CQ0. And remember, CQ0 is the standard complex plane CQ. So this is a co-limit over Q. Look at n planes in CQ. CQ sits inside CQ plus 1 by adding 0 in the last coordinate. So an n plane in CQ is also an n plane in CQ plus 1. Take the co-limit, that's the infinite Grassmannian, and it characterizes either complex vector bundles of rank n or principal UN bundles. Okay? The base spaces are the same. Okay, and so in our notation, if you so the co-limit is exactly what it is. Given a space W in CQ0, you send it to W plus 0 in CQ plus 1, 0. Okay? The standard thing. So I'm not going to write that down. So B, this is just a recollection. We do have a map TK from C infinity minus infinity to C infinity minus infinity. And what this does is that if you give me an infinite tuple, I have to say what is TKZ at I. And I'm going to define this to be Z I minus K, right? Okay. So one can check with the usual topology of union over C infinity minus infinity. These things are continuous. Okay. The continuous isos, let's put it that way. Continuous isomorphisms. T0 is obviously identity, and Tk composed TL is TL composed Tk is T of K plus L. Okay, so this is fairly straightforward to check because the topology is defined to be generated by the finite dimensional Cn sitting inside this, and the translation map is a continuous map. Okay? So it passes to a continuous map, and in the infinite setting, it's an isomorphism because inverse of Tk is T minus K. Okay. All right. So all fairly standard things. So we now sort of define for n, n a non-negative integer, we define these maps. And this is just something you may have seen already. So we want to talk about BU, right? The classifying space of U, not of UN. So how do you do that? Well, you have to imagine BU to be a co-limit of the BUNs or a direct limit. So what do? You start off with something in here. Again, same thing. You start off with some W in here. So this W, remember, lives in Gn of C infinity 0, right? Now what do? Well, you have to produce out of this n plane sitting in C infinity an n plus 1 plane. So what do? Well, you shift W by 1, apply T1 to W. So that is going to be an n plane sitting in Cn plus, it's still in C infinity, but it does not have the first coordinate, and you simply insert, and the 0th slot is 0 because you have shifted everything, and W came from C infinity 0. So C infinity 0 means that everything to all the tuples which are indexed by -1, -2, everything is 0. So if you shift it once, all tuples indexed by 0 through that is gone. So this is going to be a copy of C, direct sum T1 of W, and this now is genuinely an element of Gn plus, Gn plus 1 of C infinity, right? So this is an element here. Okay. So essentially you have an n plane, you shift it because you think of them as parameterized by tuples, shift it to the right by 1, and you insert a copy of C. So this is now an n plus 1 plane, and you define your BU obviously. So you define your BU with a co-limit of BUNs, co-limit through these maps, obviously. Okay. All right. Okay. So here's and then we need a couple more such one-line, two-line constructions. So just bear with me for the moment. But this is a space that we're actually going to need. This is called BU tilde. See, the sort of thing with giving so-called elementary proofs would be you have to sort of nail down some of the identifications and isomorphisms through explicit maps and so on. So such is the nature of things. So here, this is going to be all W, which are again in C. So these are subspaces of C infinity minus infinity, but it has this property that should. Okay. So this is a space which is all subspaces W of C infinity minus infinity, which are contained in CQ infinity for some Q strictly less than infinity, and contains C minus infinity P for some P strictly bigger than minus infinity. So this is a new space, and the point of this is that there's a proposition coming. So what is the proposition? So the proposition says that there is going to be a So we're going to use this model of Z cross BU and not use Z cross BU per se. So we are going to use BU tilde as we're going to show that the E over U that we construct will have fiber BU tilde. And because of this, it's the same homotopy type as Z cross BU. Okay. So what is the map? So let me give you the map so that it's clear what we're constructing. So what do you have to do? So sort of proof again, you have to sort of check through all the things. So the proof in the paper is like a page long because it goes through two intermediate spaces. I'm going to extract from that a direct map, and then again to show that that actually is a homomorphism, we might have to still consider those intermediate spaces. But the map is fairly standard. So remember, an element in BU is a coelement of BUNs. So an element in BU is not going to be a W, it's going to be W up to the identification of it in the column, right? So an element is of the form L comma the class of W, where W comes from some BUN, and this class indicates the class of the coelement of W, right? Okay. So where does it go? So it will go to, and I'll exactly give you where it goes to. This is going to go to, oops, sorry. So this is going to go to T, let's see, you want to put a 0 minus infinity, direct sum Tk W mod Ck 0. This and then okay, so now I have to explain to you what this thing is, right? So the point is, if you give me a W from BU, okay, so for any representative W coming from, so this W comes from some BUN, right? Because it's an element of BU. I find the largest integer K such that this is contained in W, which means C0K is contained in W, but C0K plus 1 is not contained in W, which means you're looking for the largest copy of C to the K. CK0 is just C to the K placed in 0 through K coordinates and 0 elsewhere. So finding the largest K for which this thing happens, and this by definition is going to be the orthogonal complement of C0K inside W. Okay, so look at the orthogonal complement. So essentially, W mod C0K in our notation essentially is just things which do not have anything in the first K plus 1 slot. So when you apply Tk, you're moving it down by K, and then you're adding to that C minus infinity 0. So potentially everything on the indices parameterized by negative integers, and then you're applying TL to that. That's what this entire thing is saying. Okay. Okay. So and then you have to check that this is actually a homomorphism. Okay. So that's a, I mean, that's not a proof, but it sort of is the construction. Okay. Okay. So this is one proposition. I'm going to outline a couple more constructions, and then hopefully we'll be able to state the construction of E. Okay. Okay. So we have the exponential map, which is from MN C GLN C. All of you know this. What is this map? This is the map E goes to A goes to E to the A. Just exponentiate a matrix. When you exponentiate a matrix, the determinant of E to the A is E to the trace A, and hence it's invertible. And this is a map all of you have seen many times. So this has the usual property that when you conjugate an exponential matrix, that's the same thing as conjugating either E to the TB T inverse is T E to the B T inverse. Okay. But there's a related map here, which is I look at the exponential, which is restricted to this space. And what does SK stand for? SK simply stands for, what happened? Sorry. Yeah, sorry about that. So SK stands for skew Hermitian, right? SK stands for skew Hermitian. So skew Hermitian, remember, means that A star is minus A. So an element here, A, such that A star is minus A. That's what this is. And I'm claiming that the exponential maps skew Hermitian matrices to UN. Why is that? Well, here's a quick proof. You look at e to the A whole star. Well, this is e to the A star, right? But this is e to the minus A. So this implies e to the A times e to the A whole star is identity, right? That means e to the A is a unitary matrix. So this exponential map actually lands in the unitary matrices, okay? And in fact, this space here itself, this space is isomorphic to what I'll call Herm and C. So these are the Hermitian matrices. What are they? Well, they're going to be A such that A star equals A, right? So skew Hermitian is A star is minus A. And so there's a correspondence between them. You simply basically, so what's the correspondence here? All of you know this. A Hermitian matrix can be sent to a skew Hermitian matrix by simply sending A to IA, so that when you take a star, it's a minus. So we're going to put a scaling factor of e to the 2 pi IC, right? So a genuine map here is going to be, you take sort of a, so take a C here and send it to 2 pi IC, and this is going to be so this is the isomorphism of vector spaces. The Hermitian n-cross-n matrices and the skew Hermitian n-cross-n matrices are isomorphic. And this is, by the way, a real vector space. Okay, so note that this is a real space. Okay, okay. So, well, inside the Hermitian matrices, we have inside here, we have what I'm going to call En. And this is the starting point of constructing the E. So what is En? So En by definition is going to be, you can imagine, C belongs to all Hermitian n cross n matrices such that the eigenvalues of C lie in the interval, so that the eigenvalues of C lie in the interval, closed interval 0, 1. So looking at this particular subspace, okay? So we need two properties about this, and I'll outline both of them in a proposition. So let me do that. So this is again a proposition, if you want to call it that. One is En is contractible. The other one is, if you look at, there's a map from En to Un. What is the map? You can imagine what the map is, right? Start at an element of En. It lives inside the Hermitian matrices. Apply this 2 pi I scaling to land into skew Hermitian thing and then exponentiate. So that entire composition is a map. So if you write it down succinctly, this map is literally nothing but this map. Okay. The claim is that this is a surjection. So don't need all of Hermitian matrices. It's enough to look at Hermitian matrices whose eigenvalues lie in the closed interval 0, 1. And not only that, there exists a G from, so I call this Pn, okay? So Pn inverse of some element U in U to, let's say a bijection or a homeomorphism to yeah, so they sort of warned you, it looks like a whole bunch of constructions we're doing one after another. Just have to sit down and at some point stare at this and see that things make sense. So I'm claiming that En is contractible, Pn is onto. Pn is onto is a deep down is a very basic linear algebraic fact once you use diagonalizations and so on and so forth. And G requires a little bit of work. So what is grass of this thing? So kernel of U minus I is a vector space, and grass of a vector space is the Grassmannian, the full Grassmannian of all finite dimensional subspaces of that vector space. So this, by definition, is the Grassmann of all finite dimensional vector subspaces of kernel of U minus I. So it's a union of GK of kernel U minus I over K. Okay. So I'll not sketch the proof of G, that requires some work, but I'll definitely give you a sketch of the proof of the first two. Again, proof. So the fact that En is contractible is rather easy. Do the same thing. What do you do? Well, you want to stay in Hermitian matrices as well as having eigenvalues between 0, 1, and 0, 1 is a convex set. So there you go, right? So C comma T, nothing but 1 minus T into C. This is a Hermitian matrix because T is a real scalar and it does exactly what it does. So 1 minus T into C will be a Hermitian matrix whose eigenvalues are still enclosed 0, 1. So this is a contraction of En to a point. And the fact that it's onto is basically linear algebraic check, and the construction of G requires some work. But that's one of the propositions. So I've seen two propositions. One, we replace Z cross BU with BU tilde. The other one, we have constructed these ENs which are contractible, mapping down to UNs. So now you can imagine what you want to do. You want to stabilize this construction, right? You want to stabilize the ENs to get some colimit, stabilize the UNs to get U. And maybe if you're lucky, that is the fibration P. As you will see, that is not quite the fibration P, but then you tweak the colimit En to construct another space E, which will be the final space. Okay. So are there any questions so far? Okay. So the point is you want to stabilize this because you want to get something over U, and so far we have constructed ENs over UNs, and ENs are contractible. So when you take colimit of ENs, that will also be contractible, but the fiber has to be Z cross BU, or fiber has to be this space BU tilde, right? So that's where we're heading towards. So this is E. So now let me call it F. So this is stabilizations. Okay, so you have a few standard maps. This is rho, this is not P. N plus 1. This will go from En to En plus 1. And what does it do? Well, if you give me a C, a Hermitian matrix, I'm simply going to send it to C 0, 0, C, right? That's it. And I also have these ones, and this is going to go from UN to UN plus 1. And what does it do? Well, if you give me a unitary matrix U, I'm going to produce another unitary matrix of one higher size, and you all know what to do. You just stick in a 1 in the block diagonal form. So what is the point of these two stabilization maps? Well, the point is that there is this the obvious diagram commutes, and you know what I'll write. So you can go from here to here using rho n plus 1. You can go down using Pn, which is exponentiating, and you can go from here to Un plus 1 by sticking in a 1 at the diagonal. So you see exponentiating matrix like this, because in the block diagonal form, it's exponential of 2 pi IC, exponential of 2 pi I0. So that's precisely in this form. So it's not a surprise that this commutes, but these are nonetheless things one has to check. So this commutes. So this will tell me that there's going to be some map when I pass to this limit, co-limit, sorry, right? And I'm going to call this map P prime, because the map that we are after, we have called it P, and it's not going to be the co-limit of, so P prime is the co-limit of the PNs, but I'm not calling it P. And for reasons that will sort of be clear. Okay, so this, we're almost done, but this colimit ENs is not the space E. Okay, so this of course is by our construction or by definition the space U. Okay? So now we're going to sort of, so there's something you have to check. It's like half a page of check. So you look at the fiber of the map P prime actually turns out to be homeomorphic to this thing. Okay, so this is not quite, so it's the union of BURs, R bigger than or equal to 0. So you might say, okay, did I write this? I check. I believe by construction, yeah, it probably is a disjoint union. I'll just have to check that. But anyway, I'll maybe rectify the notes. But the point is, either way, this is not Z cross BU. What you want is Z cross BU or some version of that, which is BU tilde. Okay, so you have to rectify this, and so not take the colimit of VNs, but this kind of leads to a construction, and I'm going to finally write down this E. So what is the E that you finally write down? So the E that you finally write down is, you say, okay, I'm not going to look at this, but I'm going to use that as a motivation. I'm going to look at all C. So sorry. So C is a Hermitian operator, if you want, of finite type. And so these are again all happening in C infinity minus infinity, okay, of finite type, and with eigenvalues in the closed interval 0, 1. So what do I mean by things of finite type? So the point is that if you start off with a C, this is a Hermitian operator in C infinity minus infinity. So of finite type means that this really looks like the 0 operator on R, on minus infinity to R, and then it's some genuine C tilde, an actual finite Hermitian operator on a finite dimensional vector space, and then the rest is again 0, right? So essentially, what is C tilde? So C tilde is a genuine Hermitian operator of size S minus R cross S minus R, okay, on, you can guess where it is. It's going to act on this. So these are the kind of C's that I want to choose, along with the fact that the eigenvalues of C are now going to be eigenvalues of C tilde, and they lie in the closed interval 0, 1. Okay. So once we have said all of this, now we can state their theorem, restate that theorem rather. And so if I restate that theorem, what does that theorem say? So if I go back, I don't know what color I used just to be consistent. Yeah, theorem Aguilar and Preto. So what they're saying, so now I can state it here. So what they're saying is E to U. Okay, there is a map. The map is, so this is the map they're calling P. C goes to e to the 2 pi I C. Again, when you exponentiate this, it's going to be ones apart from a small block. And so this is the map which they claim is quasi vibration. Yeah, vibration is something which says that the relative homotopy groups of E comma the fiber with respect to a base point is isomorphic to the homotopy groups of the base, and it will have long exact sequences and all of that, but you're not imposing homotopy lifting. And this was a concept, I think, introduced by Dold and Tom for certain constructions that they're doing, including constructions in classifying spaces and so on. So it's a quasi-fibration, and E is contractible, and oops, sorry, and P inverse of little u, P inverse of any, let me call it a fiber, Yeah, sorry, and P is this, which as we saw is nothing but that cross. Okay. This is essentially what you sort of have to, or what Aguilar and Preto in fact shows. Okay. So now once you combine this with the homotopy lifting and the fiber bundle kind of observations we made, you're saying that the fiber of such a bundle is homotopy equivalent to the fiber of the path space bundle, which is omega u living inside pu mapping to u, and so omega u will be homotopy equivalent to the fiber of this map, which is further homotopy equivalent to z cross pu. Okay, so yeah, so maybe I think I'll stop here. There was, yeah, I mean, I don't want to talk about equivariant K theory right now. That would sort of lead us astray to what way. So yeah, so modulo some of these details, this is, I would say, a fairly elementary construction of a bundle, and then have to check some of the details which require some work. But this proves that omega u and z cross bu are homotopy equivalent, and then you can deduce Bott periodicity using the first slide of this talk where we outline what goes on. Okay, so maybe I'll stop here.
Okay. So are there any questions? All right. There seems to be none. Anyway, thanks a lot for this lecture. Kindly share the notes with me.
Yeah, I will. Yeah, I'll just check for the typos and I'll send it to you.
Sure. Okay. Then we're signing off today.
Yeah, thank you. It was nice giving these talks.
I hope it becomes helpful in future as well. Like
Sure.
this is going to be posted on YouTube. I'll share the link with you as well.
Sure. All right. Okay. Thank you,
Bye bye.
and bye everyone. Yeah.